Good day, Math 30-1s. Today we begin a conversation about Chapter 9, Rational Functions and Equations. The best way to maybe introduce rational functions and rational equations is maybe to talk about a very convenient application. Let's imagine you are buying something online and you bought one item, and we can talk about its cost for that item, or cost per item. Now imagine for a moment this item cost $8 and there was $4 for shipping. Now $4 for shipping means you've got a total of 8 and 4, $12 for this item. But imagine what would happen if you bought two items. All of a sudden there's some sharing of that shipping cost. And so maybe you've got 8 and 8 is $16, 16 and 4 is $20 that you're sharing between two items, so the cost per item goes down to $10. The marginal cost means we've gone down $2 as a cost per item. So if you're buying multiple items, you might in a way be saving money. So now it's 8 plus 8 plus 8 is 24, and 4 is $28 for 3 items, gives you $9.33. You can see that the cost per item seems to be going down because you're sharing that shipping cost. And lastly, if there was 8 times 4, $32, and 4 is $36 divided by the 4 items is $9 per item. And all of a sudden, if you were to sketch what this roughly looks like, you've got $12 per item. Let's just do a quick $12 per item, and then it goes down to $10 per item. The scale is inappropriate, and $9.33 per item, and then $9 per item. And what starts to happen is we level off a little bit, and eventually around the sort of $8 mark, you'll start to level off, and you'll never get cheaper than $8, but all those shipping costs eventually, when you're looking at 10 items and 100 items and 1,000,000 items, the shipping becomes almost negligible. So this is the idea that we're starting to get into in our Chapter 9, combined with Chapter 10 for Unit E, Rationals. So when we're looking at this chapter, it does have this word rational that keeps showing up. So the first lesson today talks about exploring rational functions using transformations. In fact, this is the last time we sort of delve into transformations for the course, our last time. And we get to approach it in it's almost a simplified way, because rational functions, transformations, are a bit simplified. Now, what is a rational function? This is actually a chapter in grade 11, 20-2 rational functions, but most people tend to sort of forget. A function that can be written in the form of p over q, where both p and q are polynomials and the bottom's not 0, is a rational function. So polynomial on the top, polynomial on the bottom. The most basic rational function I could think of is 1 over x, a constant function over a linear function. I could again keep making up examples, and I'll say there's a quadratic on the top, not even factorable, and maybe there's a cubic function on the bottom, and again, just random quadratic over cubic. You can pick a constant over a quadratic if you wanted. As long as you've got a polynomial over a polynomial and the bottom's not 0, you're good. Okay, so you're looking for constant, linear, quadratic, cubic, quartic, quintic, any of those on top or bottom, great. What is not then a rational function? Well, I could throw in an exponential over a radical function, and all of a sudden, of course, both not polynomials. You could throw in a trig function on the top, and then a quadratic on the bottom, and as soon as you've got something that's not a polynomial, it all falls apart. Now, rational functions typically have similar things happening because we're dealing with letters or variables on the bottom, which makes it rational. We're going to have some restrictions, and with restrictions often come asymptotes. Now, there is a very typical shape that we can kind of deal with. So what I'd like us to do is to start to graph a few points to get a base function. We've talked a lot about base functions before. Some base functions we've talked about already are the square root of x. We've stretched and flipped and done stuff to that. We've taken x squared, especially last year. We've taken 2 to the x. We've taken sine of x. We've taken a lot of base functions and done stuff to them. Here is today's, and in chapter 9, the base function for a rational function. So I'm going to pick a few values, and I'm just going to start to plug them in at kind of random, and then we'll just sort of start to see what happens. 1 divided by x. 1 divided by -4, -1/4. 1 divided by -3, -1/3. -1/2, -1. And I stopped. I didn't write a 0 just quite yet because 1 divided by 0 doesn't actually work. So as we start to graph, again, without the table of values, still quite easy. Plug in a -4 and be careful with the scale. I've got this broken down into quarters. So plug in a -4. 1 divided by -4 is a -1/4. 1 divided by 1/3 is a -1/3. 1 divided by a -2 is a -1/2. 1 divided by -1 is a -1. 1 divided by 0 does not exist. And I'm going to draw a dotted vertical line indicating this doesn't actually exist right here, and say, well, maybe what happens between 0 and -1? So I'm going to pick a few values like a -1/2 and a -1/4. What happens if I take 1 divided by a -1/2? You're very welcome to try this in your calculator, but 1 divided by 1/2 is a 2. That's negative. So if you plug in a 1/2, a 2 comes out. All this is negative. If you plug in a 1/4, 1 divided by a 1/4 gives you a -4. So plug in a -1/4, out comes a -4. And all of a sudden, we've got this nice curve that starts to happen. In fact, if you imagine plugging in a -1/10, a -10 comes out. So if you get infinitely close to this x equals 0, you're going to be traveling quite the way down. Imagine plugging in a -100th, you'd be down at a -100. There is a vertical asymptote that's happening here, and as you plug in values like -5, -6, -10, and so on, you're saying 1 divided by a -10, a tenth. 1 divided by a -100, -100th. They all keep getting closer and closer to 0, but on the bottom side. So at 0, we can say, does not exist, no value. We can kind of be symmetrical on the positive x side and pick the same values as we work our way out and say 1 divided by a 1/4, 4. 1 divided by a 1/2 is a 2. 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 4. And so I'm alternating between fractions and decimals here. They're all the same thing. But I tend not to use a table of values to sketch this. You don't have to. 1 divided by 1, x is your input. 1 divided by 1 is 1. 1 divided by 2 is a 1/2. 1 divided by 3 is a 1/3. 1 divided by 4 is a 1/4. 1 divided by a 1/2 is a 2. 1 divided by a 1/4 is a 4. And this scale was intentionally set to go up to 4 because it's nice to work with. And there is your rational function, which we will eventually stretch and flip and translate and move around the place. So this gets us into our standard notation for transformations, which is a little bit less maybe crazy. We're taking 1 divided by x, stretching it by some letter a vertically. The input x is on the bottom, and so we again have our horizontal shift, which is happening left or right. Again, thinking backwards of that sign that you see there. K is still your whatever's happening here. It's then saying let's just move it all up. So K is your vertical shift up or down by whatever the sign says. Now you might notice that there's no b value attached to here. Imagine if I said something like, and this is just a side example, what if I said vertically stretching by a factor of 2 and then horizontally stretching by, and I threw in a number there, and I said, well, there's a 4 hanging out in front of this x. Technically, these could come together to be a single 2/4, a half on the top. So the a value and the b value seem to all be coming together into one parameter anyways. So instead of saying there's an a and a b, we now just get to say there's an a, which is nice. So under example 1, we've got some characteristics, and they're all really tied closely together. I see a vertical stretch by a factor of 6, 3 to the right, 1 up. So you're envisioning this rational function, base function, stretching vertically by a factor of 6. The vertical asymptote is shifting 3 to the right. Your horizontal asymptote, which was the x-axis, is shifting 1 up. What is your non-permissible value or restriction? The restriction is the denominator that x cannot be a 3. What's your domain? Well, in this base function, you go forever left, forever right, except where your asymptote is, which we sort of already defined as your restriction. So your domain is that x is such that x cannot be 3, but it could be anything else. For your range, this graph goes forever up, forever down, except for this asymptote. So your y values are such that y cannot be this shift up to 1, but it could be anything else. Decimals, fractions, we're all good. Equation of the vertical asymptote, this is an x that equals a 3. Your equation of the horizontal asymptote, this is a y value that equals 1. Now as we start to apply these transformations, this does get to be nicely tidied up. Our horizontal asymptote is attached to the vertical shift. Our vertical asymptote is what's moving 1, 2 to the right. I'm going to draw in our vertical asymptote 2 to the right, our horizontal asymptote, which is shifting 1 up, because what's happening is there's going to be a vertical stretch by a factor of 2, and this shape is going to move to this new location. So I'm simply going to say, well, let's go to this new location and sketch a vertical stretch by a factor of 2. We're going to actually avoid mapping notation to do this because we don't really need it. I can say typically we're traveling, if we ignore the original axes and say our new origin is centered right here, I can say, normally when I travel 1 over, 1 divided by 1 puts me at a 1. Normally if I travel 2 over, 1 divided by 2 should put me at a half. But you know what? This is not actually the shape because we're vertically stretching by a factor of 2. So what we're going to do is we're going to use a really dark red pen and say we're vertically stretching by a factor of 2. We're vertically stretching by a factor of 2. And we're kind of traveling through here. There's really not a lot of space left up here, so we're going to try the rest of this down here without drawing the base function. Normally if we travel 1 over, 1 divided by 1 is 1, again in the negative direction. But without putting this dot here, I'm going to say we're vertically stretching times 2. 1 divided by 2 should put us at a half, but we're stretching times 2 to a 1. Normally 1, 2, 3 over should put us at a third, but we're actually at 2/3. Normally 1, 2, 3, 4 over should put us at a quarter, but we're stretched times 2 to a half. A half should put us at a 2, but we're stretched to a 4. Now remember, we're ignoring the original axes as we do this, and we draw this in a new location. So this is a way of drawing some stretch without having to do mapping notation. And this is what transformations sort of becomes. As you flip it over, we get into something that's a little bit strange. Now, what we have here is a rational function, linear over linear. What's a little bit challenging to see is what are the transformations, because often you're going to be asked for the characteristics. Unfortunately, we're not in this standard notation for transformations. But I can look at this and say this is shifting 2 to the right, so I kind of know that this denominator is a 2 to the right. It's a restriction on 2. But what's not obvious to me is that there's a vertical shift of 1. That does not appear obvious in this example. There is something that's kind of unique that can be done. We can actually convert this form by creating two separate fractions and breaking this one fraction apart. To do this, we have to sort of literally examine a way to break this up into two separate fractions, and it's kind of interesting. I'm going to introduce the perfect number on the inside to create an x minus 2 fraction. So I'm going to write an x minus 2 and then a plus 2, which actually allows us to say here is a sharing of denominators. I know this is quite strange, but there is a sharing of denominators. I'm going to take this x minus 2 over x minus 2 and separate this from a 2 plus 5, 7 over an x minus 2, which allows me to write 1 plus 7 over x minus 2. I'm going to write this one more time, taking up a little bit of this space, and say y equals 7 over x minus 2 plus a 1. As I said before, it wasn't initially obvious that this is a vertical shift up 1. Now it is. There's a vertical stretch by a factor of 7, but this 1 was not obvious initially. So if we were to try one more, I could say leave a bit of space in the middle, and let's try to introduce an x plus 1. Try to make the bottom appear minus 1 to balance it. Sharing of denominators is an x plus 1 over an x plus 1. And then minus a 7 over an x plus 1. This gives us, if we write this part first, a negative 7 over x plus 1 plus a 1. Alright, so I know this is vertically stretching by a factor of 7. There's a vertical flip. It's shifting 1 up and 1 left. It's a very, very strange approach. I understand that, but it is a way of converting forms. Under try 3, this one's a little bit extra special, where we have to introduce the perfect number, and this time it's not going to be an x minus 2, it's not going to be a minus 2. If you do try that, you'll run into a lot of trouble. I'm going to introduce a different number, which you'll see why it works in a moment. If I break this up, I've got a 4x minus an 8 over an x minus a 2 plus a 3 over an x minus a 2. The reason for this choice is because for this fraction to cancel, a 2 there wouldn't cancel if you take that 4 out. There's not enough. So if I do now take the 4 out, now I'm left with an x minus 2 factor and a 3 over an x minus a 2. Those cancel, and in fact, now we're left with a 3 over an x minus a 2 plus a 4. Vertical shift up 4. Lastly, determine the equation of the following rational function. I can look at this and say, you know what, there's a vertical asymptote. This has shifted 3 left. I can look at this and say there's a horizontal asymptote up 2. This is shifted up 2. And I can say that y is equal to 3 to the right, 2 up, and then I have to figure out my vertical stretch. Sometimes it's obvious, sometimes it's not. Many will be able to say, you know, 1 over should be 1 up, but we're actually 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Is that a vertical stretch by a factor of 6? Should be 1 up, but 2, 3, 4, 5, 6. Should be 2 over, should be a half up, but we're stretched up to a 1, 2, 3. Gets a little bit tricky, so there's a way of avoiding maybe this confusion. Let's pick a value that we know that this equation goes through, a point, and then use it into the x, y positions to determine a. I know that this goes to the origin 0, 0. I also know that it goes through 5, 5, and maybe a couple of other points, but 0, 0 is a really nice point to work with. So I'm going to plug in a 0 and see if we can solve for the parameter a. The negative 2 the 2 can subtract over and become a negative. The negative 3 can multiply up there by the 6, which gives us, in fact, it was an a value, a vertical stretch by a factor of 6, giving us our completed equation. Probably the most strange thing that was occurring today was the conversion from a non-standard transformation notation into a more standard notation, I guess. And so these 3 questions were a little bit weird, but it's worth practicing in page 442. Otherwise, we were talking today about the base function for 1 of x, what is a rational, talking a little bit about characteristics and sketching, and then lastly, really just trying to interpret graphs or interpret non-standard notations. That is your first lesson in rational functions. Good luck.